Я совсем пропал.
Ну, все, вся командировка сейчас перед фуком. Онлайн не есть.
А?
Онлайн он есть. Good afternoon, PCS members and friends. Today we have a scientific seminar, and our scientific host today is Professor Sergey Flach, who will introduce our speaker.
Okay, thank you. So it's a pleasure to have Juan with us again, who visited already PCS last year. And I think the outcome, a partial outcome of this will probably be part of his talk. Maybe just a few words to those who haven't met him before. Juan comes from the University of Sevilla. He did also there his master and PhD, and then he rose through the ranks where he's now a full professor and runs, I think, a group, I forgot the name, on nonlinear systems or similar. So he's an expert in nonlinear dynamics, many body systems. And I think we met first time also a long time ago during some European activities on localization and discrete breathers and nonlinear lattice dynamics, which is apparently also part of today's talk, as we can see. So Juan is going to be here until December 10th, if I remember correctly. So quite some time. So feel free to chat with him for more science and other things. And with that said, the floor is yours. Let's welcome the speaker.
Well, actually, I met Sergey Flach, I think, in 2000 in the first meeting of the European network called LogNet, localization in nonlinear systems. And it was in the Houche in France. I think that was the first time. And then we have met many times, but we really didn't collaborate until I came last year in 2024. I came last year and we started to collaborate directly. I really am grateful that Sergey invited me, and it is actually a picture of our first hike with, I think it's Yun Kyo, Chinese researcher. And then we had the opportunity to enjoy the beautiful mountains in Korea. And so apart in not only the scientific part has been very rewarding, but also the social, cultural, and the natural part. And the other collaborator in this work is Yanis Bajas from the University of Latvia, and his specialty is algorithms for numerical integration, and he's very good in that. And so he helped us a lot for the code in these systems. I will start first with a small introduction of breathers, although I thought everybody knew very well about that, but later talk, the last talk of Sergey a few weeks ago, it seems that not everybody was so much aware. Anyway, maybe it's a small different point of view, and it can be also useful.
Juan, if you may want to use this old-fashioned pointer.
Oh, why not? But you know, only pointing this beautiful Japanese, sorry, Korean, also Japanese the same century pine tree. Which is very special in Korea, as I got to know. So this has been published in this journal Physica D, And these are previous papers we were inspired, and also one by Flach and by Urbini. And then I'll start with this idea of what are breathers, also very often called intrinsic localized breathers, or intrinsic localized modes, although I think the term is not especially good. It is very well used. It is not used because not very good, because modes usually refer to linear solutions or solutions of linear system, and then they are not. And because I think there are other intrinsic localized modes or whatever that are not breathers. So let's show, this is an example with a simulation of germanium with molecular dynamics in 3 dimensions. And then we have selected in this, I think there are 8 atoms of germanium. And what we have done is to separate them a little bit and then observe what happened with them. And what happened with them is that they start to this kind of movement, which actually resembled breathing, especially depending on the frequency of it is produced. And we can see that these 2 atoms of germanium, they have a relatively large oscillation, and the other ones, not so much. And just with this simple method, we obtain something which is going to live a long time. It's not really a sub-breather, which I will define, but it is also a long-lived vibration. And here it is the same simulation of a slightly higher frequency. And we have in this case taken a slice, and we see these two atoms vibrating with a larger frequency than the others, and it spreads. Somehow spreads not quite a lot, because we can see that these atoms start to move. The simulation is started with 0 temperature, but still in this vibration lives quite a long time.
That's in a 3D crystal, actually?
Yes, in 3D. This is just a slice to visualize it. And then we can take this distance between those 2 germanium atoms that are having the larger and the fastest vibration, and we can see analyze the frequency, and it's very clean because it is a 0 temperature, and we have, actually it's extremely clean. We have this large frequency, but you have very significant, is maybe 1/3 or something, 1/4 and 1/3 for the other harmonics. So we can see that clearly the solution is, or this vibration is nonlinear. It has very significant harmonics, and it's very clean.
Does it have only 3 harmonics, or there are more? Is that right?
I don't remember when I did this. I think maybe there are more, but they were not significant. But I don't remember at the moment.
Well, probably there are more.
Yeah,
You just don't.
but if they are important or not, I don't remember.
You just don't see them because what is the frequency?
The frequency is 12 terahertz here.
26.
12 terahertz.
12.
Yes.
Well, maybe it's just at the edge of the picture there somewhere.
Yeah, it's a bit strange in this case because we have this second harmonic is larger than the other.
Yeah, that's
so, but
Well, the third harmonic is larger than the second.
yeah.
That's okay.
Yes.
Yeah.
Yes, but I don't remember now how are the other harmonics. Sorry. So this is the spectrum or the density of states of germanium. And these small circles are experimental results, and the other are theoretical predictions by somebody. And here is our frequency. So it is well above the maximum frequency of the phonons or the density of states of germanium. So that's the key for the survival of that vibration, that it is well above what's separated, so there is no vibrating in that frequency.
Could you maybe comment the physics, because due to nonlinearities in lattice, you will have processes which allow you to transform 1 phonon to 2 phonons due to nonlinearities, and it seems that 2 phonon continuum very much, overlaps this breather frequency. Why it doesn't decay into two phonon states?
Because the picture is wrong, which you draw. Because you start from quantum mechanics. This is classical.
I think so.
But it should somehow correspond to each other.
No,
No?
the opposite you don't know. You know that that was the big surprise with quantum mechanics in the first place, right? That it didn't correspond to classical mechanics. So what you do here is incorrect.
So it doesn't, okay.
This simulation is certainly molecular dynamics, but classical molecular dynamics.
In a sense, you have here, if you want to get to this, to nonlinear physics from quantum, you have to assume that you have infinitely many phonons, which bind into one bound state, which is a classical breather. But maybe we can discuss this.
Yeah, maybe.
But maybe as your comment is very interesting, I would like to talk about that later.
I have a question.
Oh, yeah.
Is this dispersion experimentally and theoretically reproduced by somebody else?
That one,
Yes.
well, actually, is not mine.
But is it numerical or is it experiment or what is it?
Say it again. Which thing?
Is that an experimental result?
This spectrum
Yeah.
is taken from a journal. Yes.
From?
From some journal. It is
Yeah,
not mine.
but the question is whether the guys who published that paper in that journal, whether these results are experimental results based on neutron scattering maybe, or these are purely numerical calculations.
No.
Do you remember that?
These lines are
Probably theories.
are theoretical, and these are for neutron scattering.
Neutron scattering.
Yeah.
And
Are
another.
capable to reproduce this dispersion in very details. Is it true?
I think it's. I don't really study it very much, but I think it's the density of states of germanium is quite well known. I don't. It is not that there is just one single.
What is actually the unit cell of what is the lattice structure of this
Germanium like diamond.
diamond, and what is the number of atoms per unit cell there?
What is it?
Just two.
It's 3, I think.
Two.
Two,
Yeah?
yeah.
Two. That's why you have 6 bands. Okay.
That's two.
And another comment, so you have optical bands also. Okay. And another comment, maybe since you have seen second harmonics in the spectrum, that means that you don't have inversion symmetry. And that means that you also generate a zero harmonic. And the zero harmonic will kind of resonate with the zero of the acoustic bands. And that maybe is the reason why you see this slow spreading fluctuations on larger distances, which is basically just the attempt to establish a zero frequency, slowly decaying component of the same breather solution. Could be that there's an exact breather solution which has exponentially localized AC components and an algebraically localized DC component. That's maybe why you see this. Probably there isn't maybe even an exact solution.
You know better, but for me the simplest explanation it is we don't really have constructed a breather solution because it has been done by Tsironis and other people. So you just separate it and then observe what happens.
Yeah, what I'm trying to say is that if there is an exact breather solution, it will have AC components which are exponentially localized, but also a DC component, a deformation of the lattice, which is algebraically localized, very slowly decaying. If you try to excite something locally, you will see always these acoustic deformation excitations which will accompany it. Just a comment.
The fact that in molecular dynamics is obtained that breather frequency above, it is not trivial. It was, to my knowledge, done for the first time by Hixnakov and collaborators in Estonia, because you need to, I'm not expert in that, you need to have the electron density also into account, not only the position of the atoms, and then there is produced what is called a local hardening of the potential, which depends also, as you said, of a permanent deformation DC component. Yes. we will go anyway to much simpler systems, but I wanted to start with something like molecular dynamics to show that these breathers are not just exclusively we use very often, and we will use a low density system, but they appear in more sophisticated calculation like molecular dynamics, and also in quantum molecular dynamics, But one problem that you may have spotted is that those simulation it was done at 0 temperature. So this is more or less what we just have seen. We have localization, nonlinear vibration, some harmonics, a very well-defined frequency outside the phone spectrum. Typically in a solid, as we have an acoustic band, it has to be above. In other systems of lower dimensions with an external potential, it can be below if we have only an optical band or several optical bands. They can also, the typical energies obtained in molecular dynamics, they changes, of course, depending on the material. The group of, in Russia, the group of, in UFA, the group of Dmitriev, and others, they have done very different materials, from metals to semiconductors and so on, with molecular dynamics. So that changes, but to have an idea of the order of magnitude or in electron volts would be something like that.
John, I have a simple question. The periodic means the spatial periodic or temporal periodic?
Pardon?
In first line, there is the in a periodic medium. And in the first line,
This periodic meaning a crystal, yes.
spatial.
A crystal.
Okay.
Yes. So here we have also in a 3D simulation with a moving breather in a chain of in ion, actually, dynamics. So we see that they also can propagate in some strange way. The strange way is because as it is above the phone spectrum, the position of the atoms are staggered. So then the movement is a bit strange, but we can see that they also move quite well. So there are other intentionally localized modes or entities, to avoid the word modes. Well, I think that's why I'm not so much in favor of those, but it is very well established. It's localized mode as breathers. But yes, there are solitons, there's no vibration, kings, crowdions, which are similar to kings, compact tones. And then if we have also a charge, which is attached to the breather or the soliton or whatever, then we can have also different names or electrons, polar operators used by different authors. And many other things, but yes, will be some idea. So why is from a mathematical point of view? Also, it's very easy. We have in this kind of just 1D to be very simple, one dimension of atoms with some coupling, and then we have some side potential. We may have it, or also we can have maybe present or not, but let's suppose in this simple math that it is, and then we have some coupling. And this is the actual coupling, and this is just the linear part, the linearization of that, of the lattice of the Hamiltonian above. So these are the linear dynamical equations. We propose a trial solution, a harmonic solution, and we have the frequencies and in terms of the very well solution. And well, that's very simple, but anyway, here we have this a few of the phonons. And then what happens if we propose a solution which has a decaying term, also some velocity, although we know will not be relevant now. So you have some decaying. This simple solution will be like only for one side of the particle equal to 0. Then we have these equations, and for Q equals 0, we have two possible solutions. One is this for Q equal to pi, or this for Q equal to 0. And the interesting thing here it is that because this frequency is outside the phonon band, then the amplitude decreases exponentially. So that's why and mathematically it doesn't propagate, the vibration doesn't propagate into the lattice, because those frequencies which are not in the phone spectrum are exponentially amortiguated. And so this is also in 1D simulation. This is exactly that. Exact meaning that not that you have a solution which is analytical, but that you can obtain it numerically with as much precision as we want, typically a computer precision, something like 10 to minus 16. This will be for a short potential. That's why it is, the profile is more or less like a bell profile. And then with a frequency which will be below the phone spectrum.
So what's the y-axis on that plot?
Pardon?
On the previous plot, what are the axis labels?
Pardon?
That
This is amplitude, displacement,
Okay.
and this is just the position of the particle. So, mathematically done by McKay and Aubrey in 2004, they deduced that for the condition for the existence of breathers, it is that there are no harmonics of the vibration of the breather. It is not in the phone spectrum, and also that the system is actually non-linear in the energy of amplitude of the vibration we are constructing that breather, meaning that we don't have a point of zero slope in the curve of W with respect to energy or also with respect to amplitude. And yeah, actually it is later demonstrated actually by Aubrey, if I remember well, that if you have this condition for some of the variables, just then with this, there will be breathers that exist. So they are very generic. Other thing is what are the properties, but they basically appear whenever there is some linearity of how stable they are, other things. So the problem we dealt with Sergey was what happens when we have temperature, how long those breathers will survive, how long they survive, because those simulations you have seen has all at zero temperature. And then for that, a thermalized lattice, meaning a lattice in thermal equilibrium, then you have to be and define, not, of course, these things are very well known, but what it will mean in our work, what we will wish for thermal equilibrium, how to measure it, what will be a breather, how to create those breathers. And then we use different, we use just 1D system. You use different potentials, both in the coupling, both in the on-site potential. We have this S as a parameter, which by 1 or -1. With 1, it is a hard potential, meaning that breathers will increase the energy with their frequency will increase with their energy. While with S negative, also will happen here for this potential. It is also potential, meaning that the frequency will decrease with the energy or with the amplitude. And here we have the Lagrange potential for the coupling. So these are more theoretical models, easy to use. This is a more realistic model because we have the properties typically of the coupling that it becomes zero when they separate, and it is very hard when atoms become very close. And it is also, this has the periodicity of the lattice. And also a very different system, which is representing Josephson-junction arrays, and where we have, then there is no on-site potential, and this Q, it is the order parameter of the phase of every superconductor island. So they're very different, and there will be differences, but also things in common. So we do is to fit the potentials so that they have the same derivative in the equilibrium point, both for the interaction potential and the on-site potentials. we have a problem with the soft potentials quartic, because then we will go down here, and then we'll have an infinite potential well. So we have to limit our simulations and the condition that we are inside that well. And then, what is a lattice in thermal equilibrium? Or how, better possibly expressed, how will we measure easily or consider a parameter to measure and to see that the equilibrium has been achieved? And then, because the characteristic of the breathers is localization, then we have to compare the localization of a breather or the localization of a system in thermal equilibrium. And this parameter P measures, as very well, quite well known, or there are some variants, very well known, the thermal equilibrium. So this one means that all the energy is one single particle. If it is n, the energy is evenly spread among the n particles. So we did a approximate deduction. I think it's a big approximation, but it works very well. And it's to suppose that the unit, its particle, it is in thermal equilibrium of the rest of the lattice. And then it is proportional to the exponential of minus beta energy and the zeta partition function. And then we can obtain very easily that with some simple calculations at the end, that with some approximations, that the value of thermal equilibrium of this parameter is n divided by 2. So thermal equilibrium is characterized, but the equilibrium, it is something maybe anti-intuitive for me, but it is like that, that the localization it is in the half of the particles, and that is then we will use, or we will test if this condition is good with simulations. And of course, we will use the Ergodic theorem, because our average will be not in an ensemble, but in time, and also in a finite long time instead of. Should I wait?
Oh, it's okay.
Okay. So here we have some windows of simulation time, and what happens after some time, and we see that the oscillations of P is not a constant, of course, it is changing, and this red line is n divided by 2, which we have just deduced, and this is not exactly there, this is a little bit above, these 2-3 particles above. This is not, of course, this is not a definite value because it depends on the window, on the system, etc., etc. But it means that, well, P divided by n divided by 2 is a good measure because, of course, as it is changing, it's not going to be exactly in one position, but it is a good measure of the system is in thermal equilibrium, or is very close to it.
Can you remind what the difference between left and right?
Yes, this is for a hard potential, and this is for a soft potential. So this is to check that in different systems, we have basically the same results. It is not necessarily that always is here, depending on, because this is a specific realization of the simulation, a specific window, we have different result. Not always it is up above, sometimes it can be below, but generally it is above both in both cases.
Can you explain what is the initial condition?
In the initial condition, it is we do basically random velocities or random momenta, and then we left the system to evolve a long time.
But number of particles is you fix or what?
Pardon?
Number. Okay.
Yes,
I understand.
System has constant energy.
Correctly. This is you start with just a random
Yes.
velocity of each particle.
Yes.
And then look on what? What is the meaning of average of number of particles? What is the
this P?
what is n?
N is the number of particles. Let's go back a second. N is the number of particles, and P is this parameter, the total energy divided by the sum of the local energies. And this parameter is 1 when the energy is localized in one single particle, and is n the number of particles of the system when it is evenly
What is the
distributed.
meaning of particles? It's photons or what?
No,
Size.
particles is atoms or
Size.
But you fix this.
Yeah, so what is the problem? Well, you have a system of size, whatever, n.
And then
And then,
what is
and then the total energy is conserved. And then
Okay.
you have only short range coupling, so now you can write the total energy is equal to sum over local energies a little ENs. So the sum over E is little En gives you
okay.
capital E.
This means this wiggles means energy.
No, the
No,
wiggles means how P fluctuates. P is the participation number, it's the kind of like the inverse participation ratio.
even
It's not
even,
constant, it evolves in time. Right?
even at thermal equilibrium, it is not constant.
Okay.
It has fluctuations, and then, but the oscillations are a few particles around some value, and this value it is a bit about the number of particles divided by 2, which is the theoretical but approximate value we deduce as the value of thermal equilibrium, the participation number.
Temperature means this all fluctuations means how you can increase fluctuations. Just
How can I increase?
temperature or
Well,
how you introduce temperature.
There's no
That-
temperature, it's just microcanonical dynamics.
What is the beta in reduce?
Okay, yeah, previous slide, the beta.
beta,
What is beta?
beta is the inverse temperature of the system, because in thermal equilibrium, we will have
There's no beta. But the point is, there's no beta. This is microcanonical evolution, so there's no beta. So what do we do with that?
well, if the system is large, then it is like
So,
a thermal bath.
so we
For
could
the
say,
particle.
we could say we have a microcanonical evolution, and then Master Gibbs, William Gibbs, tells us that there is a Gibbs distribution. And there is a parameter which comes with it. In this case, it's just one beta because we only have energy conserved, nothing else. So then he says the distribution will be e to minus beta times this local density, and there will be some finite size corrections to that. Yes, if we forget about that, that's it. So beta is just a variational parameter. And then you can call it temperature, whatever you want, or inverse temperature.
But on the next picture, next.
But we have a system with a given energy, and we let it evolve, we'll have some temperature. That's beta.
I think next picture.
Yes.
Oh, sorry. We have this kind of fluctuations.
Mhm.
And if I want to say my beta is larger, how do we see some
If we
smaller?
increase
Increase temperature, you have more this type of fluctuation.
yes, but I'm not sure if the fluctuation will be larger or even smaller.
Good question. Maybe you.
But
Look,
this
if beta becomes larger, you get down to the ground state.
Temperatures.
No, temperature smaller,
Yeah,
quote
yes,
unquote,
yeah.
we go to the ground. In the ground state, nothing moves.
Yes,
So therefore, the fluctuations must become zero in the ground state.
but how we can produce larger or smaller?
So if you increase the energy density. I mean, ground state means zero energy, so lowest energy density, then probably fluctuations will be zero, then you go up in energy density and fluctuations start to somehow.
Just increase velocity, initial velocity.
yes,
Yeah,
increase
yeah.
the initial velocities and you increase the energy, and there is no. This is a number of particles we use to do relatively large but not very large. But we do simulations with 1,000 as well, and not significant changes in that picture. At least for the things. I didn't look, for example, at the frequency of these oscillations, things like that. Yes, we checked with different values of the energies and the number of particles. It is that our value of n divided by 2 is a good measure, although not exact, because I don't know what will be an exact measurement of that value. What does it mean? Is a superposition fluctuation or maybe an infinite average, something like that. But we don't have an infinite times. But it's not important for us. What this thing is that we see, and we'll see more simulations now in the route to equilibrium, that this is a measure which is reasonably good. Reasonably good to if the system achieve this value of maybe better we see following pictures. So what are breathers? And then we can construct breathers for hard potential or for soft potentials. We can do, but it is not very practical, and they will be no longer exact when we are at temperature. So we did another operational definition of breathers, which is simply we will produce given energy. When the system has evolved, but a time which is enough for achieve the thermal equilibrium, then we locate the position where it has the largest energy to avoid having two different localizations in different points, and there we change at some momentum so that we have exactly the energy we want in that site. So then we produce localization also in some way more interesting because it's also more physical, will maybe be the impact of a sweep particle producing the change in that momentum of a single particle. If that is a breather or not, that is, we don't know. That will be actually shown by the fact that the localization in the site, it is continuous there. Some of those changes in energy will produce a breather, some not, depending on many different things, not only on the energy, but what is exactly the configuration around, what the energy of the particles around. We don't know what happens, but so it will be, but it will be that we will see in the results what happened with that energy. So I have an example here, and that in this example with some breathers, this is time 10 to the 4, so it's relatively long time. So you can see that even if this is losing some energy, which is typically normal, but it lives a long time. And here we have that kind of picture, but it is the participation number at the beginning. It is a bit like 4. I don't know why this is a smaller system, but it is the same with larger system. So then this is a logarithmic scale because it's not too long and we don't see anything. So at the beginning we see the small oscillations, and then we have that in the length of the simulation, certainly it doesn't achieve, and it doesn't seem that going in the direction of achieving an equilibrium. It then seems that it's going to live a long time. And here, exactly for the same parameters, in this is a hard potential. Also, I know why this is the smaller system, but it is the same higher system. We can see some will arrive before, some will arrive later. It depends very much on, and always we will have oscillations. It's not that they achieve some exact value. And here are for this different kind of picture of energy density. We can see here that there is some localization, but then it's more or less disappear. And here we have this interesting phenomenon as well, that there is some hopping. The localization changes a little bit, but anyway, it remains localized. And this is also, no, this is linear scale. Linear scale for the time. So this is actually for the simulations before. Then we can see that for long simulations, one remains there and the other are shared equilibrium. So we will computationally define the thermalization time. The first time it hits the value n divided by 2. N divided by 2. Although it is not perfect because when you see this, it separates, and this is logarithmic, it separates, then a long time is far from that, but then eventually evolves. But we need a simple definition, and as we do statistics, then it doesn't have important so much what happens in a specific realization, but in the average of those.
So can I ask about the right picture just to check myself? So this means that due to the existence of the breeze on the right-hand side, you don't see thermalization in the system.
Exactly, not in that time.
Okay.
Not in that time.
Oh, so you hope that maybe later it will come.
Maybe.
But
Yes.
oh,
Yes.
Is it possible to check someone because it's a very long time?
Well, the problem is that sometimes I'll talk about that later. Sometimes the time is very low. The thermalization time is very long. Which we have here. So we have here for two different models. Let's just see this one. This is a hard potential, and what you have here is the initial localization parameter. When we just give that energy, this energy is 16 times in this case of H small is the thermal the average energy per particle, or basically it is the thermal energy of the system. So we have different values. For example, this means that initially when we produce this breather in the sense we produce a localized energy in one place. We don't know if that will be a breather or not, but some of them will produce breathers, some not. So anyway, we have here this localization for this case, and then in this case the life is like 10 to the power of 2, and we can see that there is a huge variation. This is 10 to 2, and this is 10 to the power of 8, and for the soft it is not so much variation in the thermalization time, but a factor 1,000, 1,000, something like that. So we have a very what actually should be expected, that depending on realization, we have very different outcomes, because also the initial conditions are different, the lattice is not the same, and then only what is the same is the thermal energy and the energy you have given to a single site, but everything can be different. What we can see roughly is there is that this slope means that what also should be expected, that when the smaller the participation number, the localization initial, then the time, the thermalization time is larger, but with a huge variation. And this is also happen. Here we have many different energies, but we can see that globally it happens that when the participation, the localization diminishes, we get a bigger value of the thermalization time, which should be expected, but always is a huge variation. This is logarithm scale, so actually it is a huge variation. In spite of that, when we do a large number of simulations, and typically it's like 10,000 simulations, although for some specific cases we needed more, or 100,000 simulations, then this is the error. How is called that in English? The
Error bar.
The error bar. The error bar we cannot see because the top of the bottom of the error bar are almost together. So this becomes completely predictable. Have sufficient number of realizations, then the curves are completely predictable in the sense that we can reproduce it once and again. And we have initially, we have here, it is not the only possibility, but the thing that gives us the clear picture is the ratio between the breather energy and the thermal energy. And after some value, which maybe that could be more or less the operational definition of a breather that have like 10 times or something like that, times the thermal energy, then we have more or less a quasi-linear dependence of the logarithm of the thermalization time, meaning that you have exponential dependence of the thermalization time on this ratio of the breather energy to the thermal energy. And for this case, there are here different thermal energies, different coupling, and sometimes there is some previous change in the curves that we don't know exactly the reason, or we didn't analyze. But
So can I ask you something?
Yeah.
Because I have some contradiction now in my head. So you started with some picture where in germanium you had some frequency of the breather, and it probably means that we have some solution of some particular shape. But now on a previous slide, you've shown us that there are a lot of various energies for this localized excitation. Does that mean that we have a whole family of breathers which are like different in the same setup?
Certainly, even with the stack breathers, we can construct breathers with different energies. We can typically the closer of they are to the phonon band, and then the energy is smaller, and then when they separate, the energy becomes larger. So but also a breather needs some pattern, which means that depending on when we produce the breather, what is the pattern around? For example, as where I commented for the hard potential, we'll have a staggered pattern. So maybe if when we put that energy in that breather, in that localized site, because we always choose the place which is more localized, then it reproduces the pattern which is closer to the stack breather, then we'll get a breather. If not, maybe not. Also, there are regions where they exist or not exist, or they're more stable or not, so that what happens will depend on the energy, but also of what it is around. This means that when we deliver that energy, it is not guaranteed that we will get a breather.
Mhm.
It is not guaranteed. Sometimes we'll get it, sometimes we'll not. Mhm. But we will start certainly with a situation with localized energy measured by P.
But in this case, for this plug, do you make sure that you get breathers or not?
Pardon?
For this plug,
Yes.
did you confirm that you get breathers or not?
Yes, because I didn't look at. We didn't look to the thousands of simulations. We looked at there were breathers in that range of energies, that we were able to construct breathers in that range of energies. But also, if the localization persists, in my opinion, what we will have certainly is a breather. Because there is no other entity that can appear in the system that have long life. Because if the frequency is inside the phonon spectrum, it will spread. If it is outside the phonon spectrum, it'll tend to live longer, then it's a breather. You understand my point? Anyway, also any of these pictures, here we have 10,000 of simulations at least. So there are many different things here. And we have one life long, if like this here. But the interesting thing is that for the relatively numbers, it is completely predictable in the sense that given this, we can reproduce, although the initial conditions are random, we'll reproduce once and again these curves. We do it, repeat the process, which is different initial conditions, different thermalization, producing some localization energy in some point of a specific value, given by this axis, and do several thousand simulations, and we'll get exactly the same result. So in this, particularly the hard potential, these breathers are very, very stable. Look at the times. This is 10 to 14. It's actually post.
It's not 10. This is natural log.
Oh yes, but anyways, order of magnitude. Yes.
2 to the 4.
Yes. So there are very few times that shows actually initially we were obtaining curves that were going like that, and then comment a little bit like that. Because of course we typically in a simulation we have some time to give to the simulation, and then we stop. And then we were initially we were skipping, and probably still we're skipping some of the longer simulations.
Excuse me, can you remind me what is small h?
The molecular is the average
the-
energy, basically temperature.
It's temperature.
Yes,
No, it's energy
energy
density.
per unit per particle.
It's how it's connected with temperature.
Temperature is only, beta is only eclipse parameter.
Okay,
Okay, energy density.
energy.
Yes.
Okay, and it looks like it's correct. Larger h, you have larger escape time or what?
Well, what happens is largest age, because we have here the ratio, means also largest breather energy. And that's why so the picture can be surprising because of that. But then we double the energy, but we also double the energy of the breather.
Yeah, but I mean, Michael is right. If you fix the ratio of the breather energy to the energy density of the background, then you have the dashed black curve and the solid black curve. And the solid black curve is obtained for larger absolute energy density, and you see that the lifetime goes down. So you have some
But
energy
also
density,
some-
your breather energy is 20 times the energy density. But if the absolute value of the energy density is larger, then the absolute lifetime of the breather is small.
We have to finish at 5?
No, we don't.
Well, more or less. I'll try to.
I think at some point YouTube will break down again. I have a theory why it happens.
Okay. Anyway, I will try. And so for some potential, it's a bit more strange. We have this strange curve here, and actually we repeat it very many thousands times, and it is reproducible again. So we don't really know what happens in this specific combination of coupling constants. And here we have to limit our thermal energy, because larger thermal energy, because we were discarding whenever the variable goes out of the potential well, then we will stop the simulation. So that means probably it's a bit strange. Some effects happens with that. And for larger thermal energy, and then there was too many of those cases happening. This is for the frontal contour OVA. We have this region here where actually it happens the opposite. It's meaning because of those energies, we don't have breathers, and then when we deliver energy, we produce actually that the energy dissipates faster.
Could you maybe comment on Frankel contour? I think there are these solitons which were introduced by Frankel contour. There's also local some excitations of nonlinear excitations of the problem. And you said that you can only have breathers. Why you cannot have these kinks?
No, you can have breathers. Kinks we cannot. Kinks we can have. But. What is the question?
No, the question was that you said before that we can only have breathers, not solitons. But in Frankel contour, I think it's famous because there are solitons.
There are solitons, but so if they are breathers, later we don't know. You're right.
Okay.
We have localized energy, but
so it can be both, actually.
it can be both. Yeah.
Okay.
But in the way we create them, it's difficult to obtain solitons because they are like moving. So I don't think we will produce, or it will be very rare to obtain solitons just with this procedure. But it's not not completely discarded. So this is photos here. Yes, for Josephson arrays, this system is a bit different because actually we do not have onside potential. So the deduction of that the particle is more or less isolated in contact with the thermal bath is actually not very good. because always the energy is shared with the other particles, the nearest neighbors. So actually, if we do a thermal equilibrium simulation, we see that the value is a bit separated from n divided by 2. Actually, for reason we don't know, but check out the several thousand particles, it is around 17% larger than n divided by 2, which for 64 means 6 particles above. However, with that condition or that other condition, the picture is the same, only the value for which the exponential behavior starts changes. But anyway, we have at the end this exponential behavior of thermalization time with respect to the better energy. So in this case, of course, what happens localization is a bit different, because you know these things much better than me, or at least most of you. But we have limited the current and the superconducting phase. Well, the localization will not appear in the current because it is limited, because maximum value is equal to 1. So what we have here, it is that we have the Josephson AC effect. We have localization in frequency instead of in position. And here it is a result of which are the average values of the frequency of the difference of phase. And then we see that the localization means that we have 2, because we only have the 2 connected superconductor islands. We have the frequencies and for one particle and the other, or an island and the other. And in localization is then in frequency instead of in position. And you can see here a specific simulation of the frequency of the localized entity compared with the other one, which is a curve, maybe things just 3 particles farther away. So you can see that there's localization in frequency. So some details of the computational, the thing is we have at the end to use a supercomputer, because the problem with parallelization is that we have the same opportunity to every simulation. So we cannot just, what I was doing at the beginning, to do some kind of loop, and then when one loop is finished, start again, because then we are then doing a big bias about shorter simulations. So that produces for different parameters, not parallelization, but we have to do the same opportunity to every simulation, and that meant quite a lot of computational time, especially for hard potentials. And then just to finish, some maybe consequences. It is we have checked in with experimentally that we can produce breathers or traveling breathers in different materials, and particularly in tungsten for some reason. The alpha particle will produce a current with zero bias, meaning that what is transporting the energy, it is not the potential difference, but energy delivered by some alpha particles. And this means that in a place like a fusion reactor, when we have this reaction between deuterium and tritium, but also many alpha particles are produced and also neutrons. And then to keep the reaction alive, also, again, there is a breathing blanket around of lithium, which produce, again, more tritium, but also alpha particles. We have an environment which is full of alpha particles. So those alpha particles will produce many breathers in the materials around the reactor, around the fusion chamber. And so there will be, in this, depending on the conditions for breather formations in those materials, we may have that the breathers have a long life, and then they hinder the evacuation of heat from the materials, or also maybe transport charge, and then break the insulation of some of the materials are in the system. ISIS is the neutron source in the UK, that's for Appleton Laboratory, and we have asked for time to try to see, because we did experiments only with alpha particles, if neutrons also can produce breathers transporting charge or not. And that's, I think, the end. Yes, conclusion or rest, as you already know. So the main consequence is that you can see that breathers can have a long life depending on the system, and life is roughly exponential with the thermalization time is large exponential with the breather energy. Some details we have already seen, but that's the basic conclusion. And that's all. Thank you very much.
Okay, thank you. So, questions?
Except the fission experiment,
Yes.
in a daily life, can we observe those kind of breather behaviors?
What we only know is that for this kind of experiments, we have some material, and then it's zero bias. And then when we send alpha particles, and not necessarily with this direction, then we observe a current, meaning that something which is transporting charge, and then the idea is if there is no potential bias, it means that something of the energy given by these alpha particles, which have a huge energy, but so these alpha particles will produce many things, but among them will produce, in this case, traveling breathers or traveling solitons, maybe, basically will be breathers for several reasons. And then that will travel attached to a charge, and for different considerations, there will be also others which are not attached to those to electric
But
charge.
it's also too professional, I mean.
Professional?
So your system is a classical, and then your system is classical, and the equation is classical, and then
This is experiment.
I mean, from daily life or some like a soliton can be observed in a lake, something like that. The breather can be observed in those kind of the large system.
Yes. And sorry, what's the question?
So, Chawan, so if someone gives you a talk about ultra-cold atomic gases, then you will dismiss the talk because this cannot be observed in daily life. Because in daily life, of course, in a lake you will not find ultra-cold atomic gases. So what do you mean by daily life? Maybe
Daily life means like lake.
a lake. Why a
Or
lake?
seashore.
Well, if we have
Talking about lakes, water.
Because soliton can be
similar to a breather, it should be maybe a traveling breather would be a tsunami.
It's a breather.
Well, I think this is a continuous system, the water surface, but typically it has oscillations. So I think it's something close to a breather, yeah. It travels at a much faster velocity, but would be a breather or a soliton.
No, but look, guys, I mean, we agreed that these solutions, these excitations need a discrete background, some kind of lattice. So your lake doesn't have a lattice, so bye-bye lattice, bye-bye lake. So if you have a lattice, then you are in business.
Yes.
Then you maybe are in business.
But not only a tsunami, also less dramatic. You know what are bores?
What?
Bores?
Yeah.
Bores are waves that happens in the mouth of the rivers, and these bores, because of the river going down and the tide going up, then you get solitary waves. You get solitary waves that go up a river, and it happens in many places. And now there are some places very famous in China, where from long ago they use in historical times. They use boats so to ride in the solitary wave the boat as it is called, upriver to transport goods and things like that. And nowadays, these are very popular for surfing or going for kayaking and things like that. They do that riding away. So in that sense, to avoid a discussion between breathers and solitons, let's call that a solitary wave, which is also non-linear. We can observe in very spectacular way, not only tsunamis, which are very dramatical, but also in this way, for example.
But I think the question was, where can you observe discrete breathers, which you were talking here about, and not the solitons and tsunamis and such things.
It's
Of
not
course.
that serious, so.
No, I mean, but that was a question. So what are the experimental ramifications of these intrinsic localized modes, whatever you call them?
Yes.
That's the question. That was your question, right?
Yeah, yes.
And the only thing what I want to dismiss is the statement daily life, because most of the stuff any of us deals here with has nothing to do with daily life.
Okay.
You can of course ask, what are the ramifications, right?
Yeah.
Right. But he likes your lake now. He will
Probably see that.
now show you that thing. So what is this here?
Yeah, well, it's not very good. This video you have just found by chance.
The shape.
So yeah, in the actually it was proposed about this analogy between Bose and electric charge. Some people has made the analogy of a surfer, a surfer on a board this kind of waves, a surfer similar to electric charge taken by a breather or solitary waves, because the energy does not for a motorboat, the energy comes from the motor or for the wind, but for a surfer, the energy comes just from the energy that has produced that wave. Maybe if it's a tsunami, some earthquake. If it is a board, some conjunction of a situation between the different the tide and the river. And yeah.
Okay.
Sorry.
Yes, Alex.
Yeah, thank you. Well, so on one of your later slides, we had the thermalization time as a function of breather energy, and you had the error bars were really, really small.
Say it again.
And this was, but you showed earlier some like non-breather lifetimes, and the spread in thermalization time was really long. So like plots like this, the error bars here are really small. So there's little.
This here.
Yeah.
Well, the conclusion about that we didn't. This is this is more complicated. For example, here, right? What happened here is that there are no breathers for that energies.
Well, that's not the question.
Yeah.
You ask in general why the error bars are so small.
Yeah, because
that's
the non-breather.
That's really amazing.
lifetime.
That's really amazing because things, well, we have, when we produce this energy, we have some probability of producing a breather, some probability of producing some other thing. And then at the end with relatively less numbers, then everything becomes predictable. So I don't know the numbers, but with some specific energy, maybe 25% will produce a breather, 50% some other thing. And then when we get sufficient large numbers, we get this predictable. But the important thing is that it is the average of the mean. So divided by n minus 1, standard deviation. The standard deviation of the mean. The standard deviation is order of magnitude of the measurement.
Okay,
So the mean is predictable, but the dispersion is huge.
okay, so if you just have a breather mode, it's thermalization time can still be over. What is this just on average as an unstable thermalization lifetime?
Pardon?
So this error bar is the error bar of the mean thermalization.
Yes.
Okay, not just the thermalization time. Okay.
Yes.
More questions? If not, then let's thank Juan again. Thank you very much. There's food outside, and remind everyone tomorrow is an IPS holiday, so Korea is working IPS not, so if you come to this place, the cafeteria will be closed. But outside, life is normal.